So last time we talked about homogeneous equations. We were talking about linear higher differential equations. If you put all the derivatives of y and y itself on one side and the function of x only on the right hand side, that's the standard form. If the right hand side is 0, then we call the equation homogeneous. And we introduce the differential operator d, capital D, to denote the first derivative. Okay. Then based on that, we can define a general nth order differential operator with all the coefficient functions multiplying the derivatives. Okay. And the nth derivative of any function can be written by d to the n y. Okay. And this d is the linear operator. And because of that, the linear combination of differential operators will be also linear. All right. So using the linear differential operator, we can write the differential equation as the operator L, the general nth order differential operator L, apply on the function y equal to g of x. Okay. When the differential equation is homogeneous, that means g of x equal to 0 on the right side of the equation, then the superposition principle applies. It says if you have k solutions of the homogeneous nth order differential equation, then the linear combination of those solutions, any linear combination actually, will also be a solution to the equation. So then we also define the linearly independent or linear independence. So if you have n functions in general, you take any linear combination of those functions, and if you can find the coefficients for those functions in the linear combination, so that the sum is 0, then we call those functions linearly dependent. Otherwise, they are linearly independent. That means you cannot find any combination of those constants so that the linear combination equals 0 of the functions equals 0. And one of the ways to test whether the functions are linearly independent or not is to use the Wronskian of the functions. Okay, the Wronskian of the n functions f1 to fn is the determinant of the matrix, where the entries of the matrix come from the functions themselves and the derivatives and the higher derivatives of those functions up to n-1 derivative. Okay. So if this Wronskian is not 0 for every of the x in the problem we consider, then these M functions are linearly independent. All right, we did a few examples last time by using this criterion to test a linear independence of functions. Okay, so let's just come back to the homogeneous equations. And we have more definitions and the theorems regarding the homogeneous equation solution. Okay, so this is for linear higher order differential equations, homogeneous differential equations. So so we're gonna have a definition here. It says any set y1, y2 to yn of n linearly independent solutions of the homogeneous linear nth order differential equation on the interval I is said to be a fundamental set of solutions on the interval. Okay. So if you have a set of n linearly independent solutions of the homogeneous equation we consider, then we call this set a fundamental set of solutions for the equation. All right. So then we have two theorems in here. The first theorem says there exists a fundamental set of solutions for the homogeneous linear nth order differential equation on the interval I. So there is always a fundamental set of solutions for the homogeneous linear nth order differential equation. All right. You may not know exactly, what this set is, but there's always one. Okay. So then the problem actually becomes to find such a fundamental set of solutions. To solve the homogeneous equation, we need to find the fundamental set of solutions. Okay. So that's what it says in the next theorem. So again, we have n solutions that are a fundamental set of solutions of the homogeneous and linear nth order differential equation on the interval I, and we call this set of solutions y1, y2 to yn. Then the general solution of the differential equation on this interval is the linear combination of this fundamental set of solutions. Okay, so so essentially that says how to solve a homogeneous linear differential equation. You just need to find a fundamental set of solutions. Okay. So then how do we find the, homogeneous, find the solution of homogeneous differential equation? We need to find a fundamental set first. Okay. Any questions? So we have a lot of theorems and definitions in this section. And one example we did last time, again, let's just review it. So we have a homogeneous linear differential equation y double prime minus 9y equal to 0, and we know two solutions, y1 e to 3x and y2 equals e to negative 3x. Those are both solutions of the equation. If you plug in either y1 or y2 into the equation holds. And we have used the Roskin of these two functions last time to, verify these two functions are linearly independent. So by definition, then these two functions give a fundamental set of solutions to the equation. So then the general solution of the differential equation will be just the linear combination of these two functions. So the general solution of the equation will be y equals c1 e to the 3x plus c2 e to the negative 3x. Okay. Okay, so that's the whole thing about the homogeneous linear differential equations. How about non-homogeneous equations? Okay. It turns out that to solve a non-homogeneous nth order linear differential equation, we just need to find a particular solution for the equation, in addition to the general solution of the homogeneous equation. So we need to just go further one more step from the homogeneous equations. All right. So what is a particular solution? Any function yp free of arbitrary parameters that satisfies the non-homogeneous linear nth order differential equation is said to be a particular solution or particular integral of the equation. Okay. So this time the function yp does not have any arbitrary constants. All right. It's a fixed function, but it has to satisfy the non-homogeneous equation. If we can find such yp, then we call this function yp a particular solution of the non-homogeneous equation. Okay. So then using the particular solution, we can find the solution, the general solution to the non-homogeneous equations. Remember, yp is just one of the solutions of the non-homogeneous equation, but we need to find the general solution or all the solutions of the non-homogeneous equation. So it turns out that you just need to add the general solution of the homogeneous equation and the particular solution for the non-homogeneous equation, and that will give you the general solution of the non-homogeneous equation. Okay. Once again, you need to find the general solution of the associated homogeneous equation. And then you need to find the particular solution to the original non-homogeneous equation and add them up. All right. So, so let me just read the theorem again to make sure you know what I'm talking about. So let yp be any particular solution of the non-homogeneous linear nth order differential equation on interval I. Okay, make sure you know what I'm talking about here. And let y1, y2 to yn be a fundamental set of solutions of the associated homogeneous linear nth order differential equation on the same interval I. So the associated homogeneous linear nth order differential equation means you just take off the right-hand side of the non-homogeneous equation and put 0. That's called the associated homogeneous equation. Then the general solution of the non-homogeneous linear nth order differential equation on the interval is y equal to c1y plus c2, c1y1 plus c2y2 plus c3y3, and so on, on to cnyn plus yp. So the first part is the linear combination of the fundamental set of solutions of the associated homogeneous equation. And the second part of yp is just the one particular solution of the non-homogeneous equation. Okay, so that's the whole theory about non-homogeneous equations. Any questions? This might be a little confusing, but we're going to see some examples. Okay, the theories are always a little confusing. So in this example, we need to verify that the given two-parameter family of functions is the general solution of the non-homogeneous differential equation on the indicated interval from negative infinity to positive infinity. Okay. Okay, so the differential equation in this problem is y double prime minus 7y prime plus 10y equal to 24 e to the x. So this is a non-homogeneous second order linear differential equation. Okay, so and according to the theorem, the solution of this equation includes two parts. One part comes from the general solutions of the associated homogeneous differential equation. So if you change the right hand side 24 e to the x to 0, then we get y dot prime minus 7y prime plus 10y equal to 0. That's called the associated homogeneous differential equation. So we need to find the general solution to the associated homogeneous differential equation. And we also need to find one particular solution to this original non-homogeneous equation in here. And the solution is actually given in this problem. We just need to verify it. Okay, this says the actual solution to this differential equation is c1 e to the 2x plus c2 e to the 5x plus 6e to the x. So you can see the first part, c1 e to the 2x plus c2 e to the 5x is the general solution of the associated homogeneous equation. And the second part, the 6e to the x, should be one particular solution to the non-homogeneous equation. So what we need to do in here is also two parts. We need to verify c1 e to 2x plus c2 e to 5x is indeed the general solution for the homogeneous differential equation. And part two, we need to verify 6e to the x is indeed one solution to the non-homogeneous equation. Okay. So we know how to solve a homogeneous differential equation, if you remember. So the associated homogeneous differential equation is y dot prime minus 7y prime plus 10y equal to 0, as already mentioned. You just put the right hand side equal to 0. So how do we find the general solution to this homogeneous equation? It's already given here. Y1 equal to e to 2x and y2 equal to e to the 5x. So if you plug in y1 or y2 in the homogeneous equation, you can see, they actually satisfy the equation. So to do that, we need to find the derivatives of y1 and y2. So y1 prime is just the e to the 2x times derivative of 2x, which is 2. So that's 2 times e to the 2x. And the y2 prime is just the e to the 5x times 5x prime, which is 5. So y2 prime is 5 e to the 5x. Then we can go further one more step to find the second derivative of y1 and y2. If you do that, you just take the derivative of y1 prime. Again, you're going to get another factor of 2 when you take the derivative of e to 2x. So then y1 dot prime will be 2 times 2, which is 4 e to 2x. And similarly, y2 double prime will be 5 times 5e to the 5x, which is 25e to the 5x. So when you take the derivative e to the 5x, you're going to get another factor 5. Okay. So then you just plug in, y1 and y2 into the equation and see if they satisfy the homogeneous equation. So just plug in everything, y1 double prime and y1 prime and y1 in here. Okay, as we already obtained those, derivatives. So if you do that, y1 double prime is 4e to the 2x, y1 prime is 2e to the 2x, and y1 is e to the x. So you can see, you get 4 e to the x minus 7 times 2 e to 2x plus 10 e to 2x, and 7 times 2 is 14. So you can see everything cancels. So it's indeed 0. So y1 satisfies the homogeneous equation. And similarly, you do the same thing to y2, and y2 double prime is 25e to the 5x, and y prime is 5e to the 5x. y2 is e to the 5x. 7 times 5 is 35. So you're going to get 25e to the 5x minus 35e to the 5x plus 10e to the 5x. Again, that also gives you 0. So y2 is also a solution to the homogeneous equation. So then you have to check these two functions, y1 and y2, if they are linearly independent or not. We already found 2 solutions to the homogeneous equation. If they are linearly independent, then we found a fundamental set of solutions for the homogeneous equation. So we can use the Wronskian or compute the Wronskian of these 2 functions and see if that is non-zero. Okay, so the definition of the Wronskian, remember, you put the 2 functions in the first row and the first derivative of those 2 functions in the second row. So that'd be e to the 2x and e to the 5x in the second row, in the first row, and 2e to x, 5e to the 5x on the second row. Okay. So this is the second order differential equation. So you just stop at the first derivative in the Wronskian. Okay. So again, how do you find the determinant of this matrix? Just multiply the upper left with the lower right and subtract the product of upper right and lower left. Okay. So that's e to 2x times 5e to 5x minus e to the 5x times 2 times e to 2x. Okay, so this is easy to do. You got 5e to the 7x minus 2e to 7x. So that just gives you 3e to 7x. And e to the 7x will never be 0. Okay, you'll never get 0 for this exponential function. So this whole thing will never be 0. So that means the Wronskian of those 2 functions is not 0, and the 2 functions are linearly independent. So that means y1 and y2 form a fundamental set of solutions of the associated homogeneous equation. So we already checked the first part. Okay, so that means C1 e to 2x plus C2 e to 5x is the general solution to the homogeneous differential equation. And then the next thing we need to do is to just verify that 6e to the x is a solution to the non-homogeneous equation. So we need to plug in 6e to the x for y into the equation, and to make sure the equation holds. Okay, so let's just do that. So this is a now example. So it's already more complicated to solve non-homogeneous equations. Okay, so I just wrote the problem again on this page in case you forget. So we got the equation in here and the solutions here we need to verify actually. But what we need to do now is to verify the part of 6e to the x is indeed a solution of the non-homogeneous equation in the problem. So once again, we need to find the derivative of yp, which is 6e to the x, and the second derivative of this function. Okay. This time it's very simple because the derivative of e to the x is just e to x itself. So yp prime and yp double prime are both 6e to the x. All right. So then you just plug in those into the equations, see what you get. So on the left hand side, we got the yp double prime minus 7yp prime plus 10yp. So that's just 6e to the x minus 7 times 6e to the x plus 10 times 6e to the x. Okay, just multiply all those numbers. 6 times 7 is 42, and 10 times 6 is 60. So we got the 6e to the x minus 42e to the x plus 60e to the x. If you combine those terms, you're going to get 24e to the x, which is exactly the right hand side of the differential equation. So that's yp is indeed a particular solution of the original non-homogeneous differential equation. See? So we have done both the first part and the second part. Okay, we have verified e to the x and e to the 5x are both solutions to the homogeneous equation. Okay, and they are linearly independent. We also verified that 6e to the x is a particular solution to the different non-homogeneous differential equation. So from the theorem, the sum just gives you the general solution of the non-homogeneous equation. Okay. So that's the whole thing about this example. Any questions?
So that was all just
That's just for one.
that was the solution.
Yeah. The non-homogeneous differential equation. We have to verify the homogeneous equation first, and then you can verify the non-homogeneous equation. Okay, so to solve a non-homogeneous differential equation is rather complicated. This is just the case of a linear differential equation only. So you can see how hard to find the how differential equation is, right? Okay, let's see. I guess I'm going to stop here. I don't think we can finish the whole section today. All right. So let's just stop here.